Close your eyes for a moment and feel the tug between your shoes and the ground. That steady, ancient pull is so constant we forget to notice it, yet it is the first force any of us ever meet. In every heartbeat, in every breath, gravity keeps its silent appointment, drawing blood home to the chest, drawing air down into the lungs, drawing every one of us toward the planet's center with a patience that outlasts empires. We call it a force, but the word already smuggles in a misunderstanding. A force, in the way we speak to children, is a push or a pull delivered by something we can see or touch. The oar against water, the wind against sails. Gravity offers no such comfort. It acts without contact, whispers without substance, bends rivers and comets alike while itself remaining perfectly invisible. Stand beneath the night sky and you can watch entire galaxies collide, their stars flung across space by a sculptor whose hands never leave the clay. The earliest observers took their clues from the simplest theater, a stone released from the fingers. Aristotle believed that stones yearn downward because the center of the universe lies beneath the ground and heavy things are homesick. His world was a place where every object had its natural address, and gravity was merely the postman delivering parcels home. For 2,000 years that story sounded reasonable, for a stone never drifts sideways when released, and stars circle reliably overhead. Yet the story left a quiet unease. Why should the same homesickness govern both the falling apple and the circling moon? The apple and the moon, those two companions of legend, were waiting for someone willing to ask the question not in a classroom, but in an orchard alive with summer scent. Isaac Newton's genius was less the fall of fruit than the patience to sit long enough for the same rhythm to echo in his mind at wider scale. Imagine the moment when the thought arrived. Perhaps the apple and the moon are obeying the same etiquette of attraction, a single rule written once and applied everywhere. In that instant, the local became cosmic, and gravity stepped forward as the invisible architect of every motion we know. Still, even Newton admitted he made no guess about how the tug traveled across the void. He gave the world an equation elegant as a blade, but confessed he could not conceive of action without touch. The force that keeps planets faithful to their orbits arrived, in his description, like a letter with no postmark, delivered but unexplained. We live today inside the same mystery wrapped in newer language. Hold a cup of tea and you feel weight because the entire earth bends the fabric beneath your feet, tilting the table, the saucer, the liquid surface into a gentle slope in time. Einstein replaced the tug with a geometry, yet even he could not say why mass bothers to curve that geometry in the first place. We have traded the word force for the word curvature, but the question remains. Who set the rule that geometry must listen to mass and mass to geometry? Everyday life gives few hints of the depths hiding just below the obvious. A toddler drops a spoon from a high chair, again, delighting in the reliable arrival of the bright metal on the kitchen tile. Parents call it learning cause and effect. The cosmos calls it the rehearsal of a principle that will still be true when the sun is a white ember. The spoon accelerates 16 feet per second every second, a whispered promise that whatever is not supported will fall, and whatever falls will fall faster as the seconds pass. That steady increase is the signature of gravity, unlike any other force we meet. Electromagnetism flings particles sideways but never commands them to accelerate without limit. Only gravity insists on gathering speed, as though falling were a journey with no cruise control. Yet even here, on the scale of spoons and high chairs, the invisible architect is already thinking ahead. If you could measure the fall with exquisite care, you would discover that the spoon and earth move toward their common center of mass, a point located roughly 4,000 miles beneath your slippers. The planet does not stay perfectly still. It rises, an immeasurably small distance, toward the spoon in the same instant the spoon descends toward the planet. Both partners obey the same invitation and both answer. Scale upward and the choreography grows majestic. The moon, 60 Earth radii distant, takes 27 days to complete its slow pirouette. Yet it is falling every moment, falling around the curve of the planet rather than into it. The sideways speed of its birth, wrought in collision and fire, was just sufficient to turn every downward inch into a perpetual miss. We see a circle, but gravity sees an infinity of tiny falls, each one redirected by the horizon racing away beneath. Scale further and the dance becomes a waltz of worlds. Jupiter, 300 times the mass of Earth, tugs the sun into a gentle wobble. That wobble betrays the presence of the giant to distant eyes, as surely as the trembling rope betrays the child on the swing. Astronomers walk rooftops at night and watch the bright star Sirius. It shivers across the decades, revealing a white dwarf companion cloaked in splendor and in silence. The invisible architect signs every contract with the same ink. The motion of the visible reveals the presence of the unseen. Still, no one has ever seen gravity itself. We witness only its handwriting, the arc of a thrown ball, the red shift of light climbing out of a well, the slow inspiral of neutron stars broadcasting ripples across spacetime like drumbeats on cosmic leather. Those ripples, first sensed in 2015, passed through Earth and stretched our planet by a distance smaller than the width of a proton. For a fraction of a second, your arms and mine were slightly longer than they should have been, though no eye could measure the change. The universe leaned in and whispered, and the whisper was so gentle that only laser light suspended in vacuum could overhear. What are we to make of a force, if force it is, that refuses to be seen, yet refuses to be ignored? Weight itself is only the collateral of gravity's true business. We feel heavy because the ground must press upward to keep us from following the invitation of curvature. Remove the ground and the sensation vanishes. Astronauts orbit in perpetual free fall, their arms floating not because gravity has been escaped, but because they have surrendered to its choreography. There is no such place as zero gravity, only zero resistance to the fall. The paradox deepens when we learn that gravity is by far the weakest of the four known presences that govern matter. A simple refrigerator magnet can outpull the entire planet, pinning a paperclip against the downward tug of 6,000 billion tons of rock and iron. Yet gather enough mass and even the weakest among us becomes irresistible. No magnet can trap light, but gravity bends starlight around galaxies, creating mirages in the sky. The force that cannot lift a nail can nonetheless lock a photon in a cage from which no key exists. Perhaps the most human response is awe at the scale of the silence. Gravity never sleeps, never tires, never forgets. It keeps the atmosphere stitched to the planet, the oceans pressed into basins, the moon locked with one face forever toward its parent. It writes tides in the blood of women, drifts continents like rafts, and will one day coax the sun itself to swell into a red giant, cradling Earth in a final, fatal embrace. All of this is done without sound, without color, without the courtesy of visibility. We walk upon a stage erected by an unseen director. Every footfall is a reminder that the universe is under no obligation to make itself obvious, only consistent. The same law that steers galaxies also steers the heartbeat of a sparrow. The same curvature that delays the return of starlight delays the reunion of a thrown ball with the patient grass. From the smallest to the largest, gravity is the single theme that refuses variation, as though the cosmos, in its earliest breath, decided upon one melody and has never seen reason to change. And yet we do not understand the melody's origin. We map its notes, predict its crescendos, even harness it to slingshot probes toward the outer dark. But why mass should curve space, why curvature should dictate motion, why the constant of proportionality should possess the value it does, these are riddles we carry like smooth stones in the pocket. Every experiment confirms the equation, but no insight unveils the reason. The invisible architect remains courteous, answering every question put to the apparatus, yet withholding the answer to the only question that truly matters. Why is there something rather than nothing for gravity to bend? Tonight, step outside and look up. The bright wanderers we name planets are sliding along grooves carved not by hands but by the patient accumulation of seconds. The arch of the sky is a dome only in appearance. In truth, it is a vast ocean of distance, and every bright point is adrift upon its currents. Gravity is the tide within that ocean, the breath that gathers waves and smooths them again. We stand on the shore, ankle-deep in starlight, listening for the sound of the surf. What we hear instead is the hush of our own pulse, a reminder that we too are built from the same material that obeys the fall. Somewhere beyond the last visible galaxy, a dwarf star is shedding its outer layers, and the expelled gas is falling back, coaxed by the same gentleness that once gathered clouds into the sun. Somewhere inside your chest, blood is falling toward the heart, completing a circuit begun in an embryo smaller than a raindrop. Between these extremes, the invisible architect continues the work that needs no tools, no rest, no praise. We may map the cosmos, name its constellations, ride its invisible rails to distant moons, yet we remain guests in a house whose foundation we cannot see. The only honest closing is a hush of acceptance. Gravity will never speak in words we can translate. It will never appear as a shape in the fog. It will only continue to hold, to bend, to gather. And we, in our brief moments standing upright against the pull, will continue to wonder what it means to be held so firmly by something we have never managed to grasp. Imagine standing beneath a lantern-lit sky in the year 1666. The air smells of wood smoke and damp wool. Somewhere beyond the hedgerows, a church bell counts the hour, while above your head the moon glides silently between drifting clouds. You have walked home from the market with a paper cone of small, hard apples, and one of them, small enough to close your fist around, slips free, knocks your boot, rolls across the frost-rimed grass and settles. It does not fall far. Yet in that moment of quiet impact lies a secret so immense it will realign every planet, every comet, every ocean tide, every heart that ever learns to count time by the swing of a pendulum. Isaac Newton, 23 years old, thin-shouldered, long-haired, sits in his mother's orchard not far from where the apple now rests. He is not thinking about apples, not exactly. He is thinking about the moon. He is wondering why it does not fall. We have heard this story since childhood, how the apple bonked the young man's head and gravity was suddenly invented. The truth is gentler, slower, and far more profound. Newton sees the fruit drop, yes, but he sees it as the finale of a thought already circling his mind like moths around the candle. The apple descends a few feet. The moon arcs across 250,000 miles. Two motions, one cause, one law, and so he begins to speak, not aloud but on parchment, in the private language of geometry. He writes that every scrap of matter tugs on every other scrap with a force that weakens as the square of the distance. Double the gap, the pull becomes 1/4, treble the gap, 1/9. The numbers feel cold, but the idea is warm. The cosmos is stitched together by mutual yearning. Earth calls the apple. Apple answers Earth. Both call the moon. The moon, in turn, calls the tides. And the tides drag the continents into a slow waltz that will outlast every orchard, every bell tower, every name once carved in chapel stone. To test the notion, Newton compares the fall of an apple, say, 60 feet in 1 second, with the fall of the moon in the same second. The moon, he reasons, is also plummeting toward Earth, but it is moving sideways so swiftly that the curve of its fall matches the curve of Earth's roundness. It keeps missing. That perpetual miss is called orbit. With only quill ink and the patience of a monk, He calculates how far the moon should drop in 1 minute if his inverse square rule is true. The answer matches the observed motion within the accuracy of the best telescopes of the age. He blinks. The moon obeys earthly arithmetic. The heavens are not made of different stuff after all. The shock of recognition spreads outward like ripples on a pond. If the same law binds the apple and the moon, then the planets must also attract one another. Jupiter tugs on Saturn. Saturn returns the pull. Their orbits slowly breathe, advance, retreat over centuries. Astronomers armed with Newton's formula can predict these breaths decades in advance. And when the planets finally arrive at the predicted places, the victory feels almost eerie, as though the solar system were a vast clockwork built to illustrate one man's homework. Yet the law is spare. It contains only 4 symbols: mass, distance, force, and a constant of proportionality, a knotted thread that stitches the units together. From these 4, engineers will one day launch steamships, suspension bridges, locomotives, and 3 centuries later, spaceships that sling themselves around Venus to reach Mercury, or around Jupiter to reach Saturn, stealing momentum from the very planets Newton once pondered. The navigator's sextant, the surveyor's chain, the artillery officer's quadrant, all become extensions of the orchard insight. Civilizations rise on the quiet confidence that the equations written in a candle-lit room apply equally to cannonballs, cart horses, and comets. But confidence is not certainty. Even Newton, solitary and brilliant, senses the shadow at the edge of his mirror. He admits that he has no mechanism for gravity's reach across emptiness. He frames no hypothesis, he writes, as though refusing to step onto a bridge he cannot see. The force acts at a distance, instantly, with no messenger. How does Earth know where the moon is, and how does it know right now? The question lingers like incense in a cathedral, sweet and unresolved. Still, the practical victories accumulate. Lighthouse lenses are ground to curves predicted by Newton's optics and held aloft by trusses calculated with Newton's mechanics. Clockmakers balance pendulums that compensate for thermal expansion, and these clocks travel aboard wooden ships to the South Seas, where navigators compare local noon with the time kept by a brass chronometer set to Greenwich. The difference in the sun's height reveals the difference in longitude, and thus the ship's place on the blank ocean is fixed to within a few nautical miles. Each sighting, each winding of the key, whispers the orchard's secret. The same gravity that bends the ship's path into a great circle route also pins the chronometer's pendulum to the deck, and both belong to Earth. By the 19th century, the law seems invincible. Neptune is discovered when astronomers notice that Uranus is wandering from its appointed table of future places. They assume an unseen planet tugging it astray. They invert Newton's equation to solve for the unknown mass. They point the telescope, and there the new world gleams, blue and calm, exactly where the sums said it should be. The public thrills to the story as though humanity had reached across 2 billion miles and nudged a giant into view. The astronomers themselves feel a more sober wonder. The reach of the mind has become longer than the reach of light from the edge of the solar system. Yet every empire of thought casts a frontier of shadows. Mercury, the swift planet closest to the sun, also drifts. Its oval orbit slowly pirouettes, a motion called precession. Newton's law predicts a pirouette, but not at the observed rate. By the width of a few arcseconds per century, Mercury arrives ahead of schedule. The discrepancy is smaller than the angle a human hair subtends at a distance of 100 yards. Yet it is enough to unsettle the sleep of those who trust that the same equation governs silver coins sliding across a tavern table and distant worlds aflame in sunrise. Still, the law is too beautiful to abandon over a hair's breadth. Astronomers propose an unseen inner planet, Vulcan, whose mass would supply the extra tug. Telescopes scan the glare of the sun during eclipses. nothing appears. The silence grows louder. Meanwhile, the clocks grow more precise, the surveys more exact, the cannon more lethal, the bridges more daring. Engineers span the Firth of Forth with steel that obeys Newton's calculus. And when gales scream down the North Sea, the lattice of girders sways but does not break, because every rivet was placed in trust that force equals mass times acceleration, and every acceleration is the straight-line echo of a gravitational tug. Yet beneath the rivets and the brass instruments, the mystery remains. How does the Earth know instantly where to pull? Does the information travel faster than light? Newton's mathematics never says. It describes the choreography, not the conversation. The law is a map of motions, not a story of causes. And maps, however faithful, are not the territory. So the orchard moment ripens into paradox. The same insight that lets us steer ships across unmarked oceans also leaves us staring into an abyss of ignorance. Gravity binds, but it binds without touch. It shapes galaxies into whirlpools of stars, yet no one has ever held a piece of it in the palm of the hand. We feel its weight when we lift a child, yet the child feels no wind, sees no color, hears no sound of the force that roots her shoes to the soil. Still, life orbits this absence. Farmers plant by tides that Newton's equation forecasts. Pilots bank along great circle routes first drawn by celestial mechanics. Every skyscraper sways at a period tuned to avoid resonating with the seismic murmur of a planet that never stops falling toward the sun. Civilizations rise and fall, and through it all the moon continues its patient drift away, 3 centimeters each year. Because the tides it raises on Earth siphon rotational energy into orbital distance. A slow divorce negotiated by the same law that once brought the lovers together. One day, long after the last orchard has returned to wildwood, the moon will be half again as far, and Earth's day will have lengthened to match the lunar month. Sun and moon will stand motionless in the same hemisphere of the sky, each gazing at the other through the silence of mutually locked faces. The same equation that let a young man in Woolsthorpe predict the fall of an apple now predicts the hush of that final tidal lock. And yet the equation itself is only a portrait, not the sitter. It tells us how strongly, not why. It offers no bridge across the emptiness, no whisper traveling the void to say, "Here I am." The force remains a ghost at the center of the machinery, a name we have given to the curvature of paths we do not fully comprehend. So we stand again in the orchard, centuries later, night air cool against the skin. The apple has rotted, fed the soil, become tree again. The moon rides higher now, thinner, older. We look up and feel the old vertigo. The same tug that brings fruit to ground keeps satellites aloft. The same summons that draws rivers to sea keeps galaxies from flying apart into lonely specks of light. Somewhere between the apple and the moon, between the drop and the eternal miss, lies the next secret. Newton's law is not the final word, it is the prologue. A deeper grammar waits, one that speaks of time bending, of space stretching, of gravity not as force but as geometry. But that is another orchard, another night. Another young mind willing to sit quietly beneath the lantern sky and listen to the stillness between heartbeats. Gravity, we have been told since childhood, is a force. A silent, invisible hand that keeps our feet on the floor, the moon around the earth, the planets in their ancient waltz around the sun. Yet if you were to ask Einstein, he might smile a little sadly and say, "There is no hand. There is only the stage itself, bending beneath the actors, tilting the footlights so that every stride, every orbit, every beam of starlight follows the curves of an unseen scenery." This chapter is about that scenery, spacetime, and how its quiet folds became, in the winter of 1915, the single most intimate companion of every mass in the universe. Imagine you are standing in a small, windowless room. Your feet press against the floor, your stomach presses against the hunger for lunch, your heart presses against the cage of your ribs. Now imagine that the room is not on Earth but in the belly of a rocket, far from any planet, accelerating at precisely 9.8 meters per second squared. Inside, you cannot tell the difference. A dropped key falls as if loyal to a planet. Your own weight feels unchanged. Einstein noticed this modest, almost banal observation and declared it the hinge upon which the cosmos turns. He called it the equivalence principle. The tug we attribute to gravity is indistinguishable from the push we feel under acceleration. Weight, therefore, is not the signature of a mysterious force, but the signature of a frame that is not free. Remove the floor, remove the rocket walls, let yourself fall, and the sensation vanishes. You become weightless not because gravity has been switched off, but because you have surrendered to the same path that space-time has already laid out for you. In that surrender is a clue. Gravity is not something that pulls, it is something that guides. To understand the guide, we must first picture the road. Picture empty space, not blackness, not nothingness, but a pliable fabric, smooth and dark as silk, stretched taut in all directions. Now place a star upon it. The fabric dips, dimples, forms a shallow well whose walls slope gently outward. A planet placed nearby finds itself on an incline. It must circle the star because to fall inward would demand a steeper surrender than its sideways motion allows. The planet does not feel a force. It feels only the floor of spacetime tilting beneath it. This is the rubber sheet analogy, overused in classrooms, yet still quietly miraculous if you follow it to its conclusion. The sheet is not two-dimensional. It is four-dimensional, three of space, one of time, woven so tightly together that to bend one is to bend the other. When you sit motionless in a chair, you are moving through time. The more massive the chair, the more the cushion of spacetime beneath it compresses, stretching the seconds so that your head ages a few nanoseconds faster than your feet. You do not notice. Your hair will not gray in the instant. But your phone, should it consult satellites, must notice, for up there the curvature is weaker and clocks tick faster. Without Einstein's correction, every navigation fix would drift by kilometers within a day. The map on your screen stays accurate because engineers continually kneel to the curvature you cannot feel. How does mass tell spacetime to curve? The answer is written in a set of 10 interlocking equations that Einstein carved onto blackboards in wartime Berlin, but the essence can be carried in the mind like a small, smooth stone. Mass and energy are the stone. The indentation they leave is the geometry. The geometry in turn tells the stone how to roll. The equations are simply the grammar of that conversation, a self-referential loop in which the speaker and the spoken are the same. We are accustomed to forces that act across a distance, magnetism, electricity mediated by invisible messengers. Gravity needs no courier. It is the shape of the message itself. Light, massless and fleet, might seem immune to such topography, yet it too keeps to the valleys. During the total eclipse of 1919, Arthur Eddington sailed to the island of Principe and photographed stars whose light skimmed the darkened limb of the sun. When the plates were developed, the stars had drifted outward by a sliver the width of a raindrop held at arm's length. The sun's mass had bent the straightest path in the universe, turning starlight into a crooked road. The newspapers proclaimed a revolution. Einstein awoke to find himself famous. But the deeper wonder is not that light bent. It is that it bent exactly the amount his geometry predicted. A theory born in the quiet of a patent office had forecast, to the arcsecond, how much a far star would appear to slide when spacetime was dented by 2 trillion tons of churning plasma. The universe, it seemed, was written in the language of curvature. Time, too, bends. Place one clock on the summit of a mountain, another beside the same sea. After a year, the mountain clock will have counted a few extra microseconds, small change, yet enough to doom any GPS satellite that ignored the surplus. Each satellite carries atomic hearts that beat faster in orbit than their twins in the Pentagon. Engineers dial in a daily Einsteinian correction. 7 microseconds subtracted for altitude, 45 added for velocity, a net drift that would accumulate 10 kilometers of error if left unloved. Every turn-by-turn direction you trust is a quiet testament that the fourth dimension is warped, that the seconds themselves are elastic. Still, the mind resists. We are creatures who evolved in flat savannas under gentle gravity. Our intuition was forged where space-time is so nearly Euclidean that Newton's straight lines sufficed. To trade force for geometry feels like trading blood for numbers. Yet consider the falling apple. Newton saw it drawn by a force across the void. Einstein saw it sliding along the shortest path in a four-dimensional valley excavated by the Earth. Both descriptions predict the same arc, but only one removes the spooky action at a distance. In that sense, the apple is freer than we first imagined. It is simply following the straightest possible path through a curved stage. There are places where the curvature becomes ecstatic. If a star collapses beyond a certain threshold, its well becomes so steep that light itself, trying to climb out, finds the walls closing faster than it can travel. A horizon forms black perfect, where time dilates toward a standstill and space tilts until forward becomes inward. We call such a place a black hole, though the name is too small for what is really a geography of no return. Fall through and the word fall loses meaning. You are not moving into a place but into a when, a future that can no longer be shared with the past you left behind. Yet even here, Einstein's geometry holds. The singularity at the center, where curvature becomes infinite, whispers that the theory must one day marry quantum uncertainty, but the marriage contract has not been signed. The universe keeps its own counsel. Back in the quiet of the solar system, the planets continue their slow spiral, not because an invisible string ties them to the sun, but because the sun has made time itself run more slowly beneath its fiery surface, and the planets, like frugal travelers, seek the route that ages them least. Kepler's ellipses are revealed as the gentlest negotiable paths through a four-dimensional terrain. Matter, in its patient aggregate, simply chooses the cheapest fare across time. We began by saying that gravity is misunderstood. Perhaps the deeper misunderstanding is the belief that understanding must feel intuitive. The curvature of space-time is not visceral. It is abstract, relational, confirmed only by the cold patience of clocks and lenses. Yet its consequences surround us in every falling leaf, every synchronized satellite, every photograph of a distant galaxy smeared into arcs by the lens of intervening dark matter. Geometry has become destiny. And so we return to the small room, the rocket, the equivalence principle. Stand there once more, eyes closed, and realize that the weight in your bones is the universe whispering that you are choosing every second not to follow the freest path. The floor beneath you is an interruption, a borrowed acceleration, a promise that as long as it pushes, you will feel the illusion of force. One day the floor will fail, the rocket will exhaust its fuel, the planet will erode. On that day, you will be given back to the curvature, to the fall that is not a fall, to the geometry that never needed the hand you once imagined. Until then, we walk upon a fabric we cannot see, trusting that its folds will hold, wondering what other quiet shapes it may yet reveal when we learn to read the warp in time itself. Imagine cupping a single snowflake in your palm. It rests there, cool and weightless, yet every flake in every winter is knit together by the same force that steadies planets. We name that force gravity. We live inside it, breathe it, and trust it so completely that the thought of slipping makes us reach for a railing without thinking. But every physicist, at least once, has felt a chill far colder than snow. Gravity refuses to be seen as a particle the way light becomes a photon. The way a magnet's tug is passed by virtual messengers called gluons or W's gravity keeps its secrets. And that silence is the loudest puzzle left in science. To understand why, walk with me for a moment beside a quiet lake at dawn. The surface is smooth, a flawless mirror for the sky. Drop a pebble. Circles flee outward, each ripple carrying energy, information about the stone's fall. In the language of quantum field theory, every ripple of any field is a carrier of force. Electromagnetic ripples are photons. Strong force ripples are gluons. Gravity, too, should send out ripples across spacetime when masses accelerate. Give those ripples a name, gravitons. They ought to be tiny packets of curvature, minuscule quivers of geometry itself, dashing through the void at the speed of light. Mathematics even predicts their spin. 2 units of angular momentum, twice that of a photon, a fingerprint unique in nature. Yet no detector has felt that fingerprint. No particle collider has caught the fleeting brush of a graviton on its instruments. The lake appears forever unruffled at the smallest scale. The difficulty is not lack of trying. It is that gravity is unspeakably weak. A household magnet lifting a paperclip defeats the gravitational pull of an entire planet. To see a graviton, we would need to measure energies so extreme that the apparatus would collapse into a black hole before delivering a single reading. Nature, it seems, has hidden her most delicate needle in a haystack the size of the cosmos. But the impossibility of measurement is only the first veil. The deeper trouble lies in the way the 2 great pillars of physics talk past one another. General relativity speaks in the continuous prose of geometry. Mass tells spacetime how to curve. Curved spacetime tells mass how to move. The equations are smooth, self-consistent, and infinitely divisible. Quantum field theory, by contrast, is a staccato of integers. Everything is countable. 1 electron, 2 photons, a swarm of virtual particles flashing in and out of existence. When we try to write gravity in that staccato language, the symbols rebel. Probability sums diverge. Infinities appear faster than they can be cancelled. The result is like trying to play Bach on a piano whose keys keep multiplying under your fingers. Each note spawns new keys, new wrong notes, until harmony dissolves into noise. So we search for a new instrument, a framework that can accommodate both the smooth and the granular. One candidate is string theory. Picture again that lake, but now imagine each ripple not as a simple wave but as a tiny vibrating string whose length is the Planck length, 10 billion times smaller than a proton. Each mode of vibration is a different particle. One particular vibration, with spin 2 and 0 mass, is the graviton. In the equations, the infinities cancel exactly, as if the extra dimensions in which these strings move provide hidden pockets where troublesome quantities neatly fold away. The theory sings in perfect pitch, but only if the world has 10 or 11 dimensions, most of them curled so tightly that we walk unaware through their hidden corridors. No experiment has yet peered into such a corridor. String theory remains a cathedral of mathematics whose doors open onto landscapes of possibility rather than photographs of reality. Another path is loop quantum gravity. Here we do not add hidden dimensions. We break spacetime itself into grains. Picture the ancient practice of making a mosaic. Instead of cutting stone into tiles, imagine cutting geometry into loops, tiny links of gravitational field lines. At the Planck scale, area and volume come in discrete pieces. Space is not an aquarium through which events flow. It is the scaffolding of events, countable like the rungs of a ladder. In such a lattice, gravitons might emerge as vibrations, collective excitations of the grid. The math reproduces general relativity on large scales, yet predicts that light of different wavelengths travels at minutely different speeds, a dispersion that might, just might, be observed in bursts of gamma rays from distant galaxies. So far, the photons arrive together, they're raced too close to call. But the possibility lingers, a whisper we keep listening for. Between these two visions, strings and loops, there are others. Causal dynamical triangulations that build spacetime from tiny pyramids. Asymptotic safety, where gravity becomes well-behaved at high energies. Entropic gravity that treats spacetime as a thermal artifact of information. Each is a language invented to describe a country no human has visited. We speak them as scholars once spoke Latin, hoping fluency will one day guide us through territory only imagination can presently map. And yet, perhaps we already feel the graviton's echo in the hush between galaxies. Cosmologists chart the expansion of the universe using distant supernovae as milestones. If a background of gravitons permeates space, their cumulative pressure would nudge that expansion, the way a steady breeze bends the stalks of a wheat field. The dark energy we observe, the gentle acceleration of the cosmos, might be the shadow of countless gravitons, their collective whisper bending the trajectory of billions of years. Or it might not. The data are still too gentle, the error bars too broad. We stand at the shoreline, watching for a tide we suspect is there because the math tells us so, but whose rise has not yet wet our feet. There is a humbling symmetry in this search. Every child who has ever asked why a stone falls has, in essence, wondered about the quantum soul of gravity. We have merely refined the question, dressed it in tensor calculus and Feynman diagrams, and set it beneath mountain ranges of machinery. The child's curiosity and the theorist's equation share the same root, the desire to know why things are drawn together. Galaxies clasp one another in spinning gowns of stars because, somewhere in the arithmetic of reality, a particle we cannot touch passes a message we cannot hear. Perhaps the graviton is a phantom, a mirage that will dissolve when we finally grasp the full grammar of spacetime. Or perhaps it is real but forever inaccessible, a candle on the horizon that recedes as fast as we sail. Physics has known such bittersweet victories before. We predict neutrinos decades before we build a detector sensitive enough to see them. We infer the Higgs in equations long before protons are smashed to reveal it. Patience is part of the method, but gravity, because it shapes the very stage on which experiments are performed, resists the detachment that allowed us to trap other forces in chambers and cloud tracks. To observe the graviton directly would be to stand outside spacetime and peer in, a vantage no creature made of mass and light can ever achieve. So we listen instead for stories gravity tells in other tongues. Two black holes collide 1 billion light-years away, and the resulting ripples, gravitational waves, wash over Earth, stretching and squeezing the kilometers of laser light in LIGO's arms. Those waves are the coherent shouts of accelerating mass. They should be accompanied by a faint chorus of gravitons, a spray of quantum noise riding the crest. But the signal is drowned in the roar of the wave itself, the way the crackle of a single ember is lost in the roar of a forest fire. Still, each detection is a rehearsal, a sharpening of instruments, a promise that someday we might separate the whisper from the shout. Until then, we live inside the mystery, and there is a strange comfort in that. Gravity keeps our feet on the ground even as it eludes our grasp. It is the reason the sun burns with a steady light, the reason Earth's crust carries mountains, the reason every atom in our bodies has been forged in stellar furnaces that were held together by the very force we cannot quantize. We are in every instant cradled by an enigma. The same force that binds galaxies also binds thought to nerve, nerve to bone. To look up at the night sky is to look inward. The curvature of space outside echoes the curvature of wonder within. Perhaps the next revolution will come from a direction we have not yet imagined, a perspective that dissolves the boundary between large and small, particle and geometry. Or perhaps we will simply learn to live on the shoreline, content that the horizon is infinite, that every step we take adds another layer to the fractal coast of knowledge. Either way, the search continues quietly, like the turning of stars around the pole, like the slow migration of continents, like the patient accretion of snow on a high mountain ridge. And somewhere in the hush between heartbeats, the graviton, if it exists, slips through our outstretched fingers, carrying its message of unity across the dark. Take a single galaxy in the night sky. From edge to edge, it spins like a slow, luminous hurricane of stars. We watch the outermost suns trail along their enormous orbit, and we expect them to travel more slowly than the crowded stars near the glowing core. After all, that is how the planets behave around our sun. Yet when the measurements are taken, the outer stars are moving far too fast. They ought to fly away into the dark, tearing the galaxy apart. Something unseen encloses each galaxy in an invisible cradle, pressing those reckless suns inward, holding the whole structure together. That quiet discrepancy, first noticed in the 1930s and confirmed countless times since, is our earliest whisper of dark matter. It is not a whisper that reached the public quickly. For decades, astronomers assumed the spinning stars were simply mismeasured, or that extra gas and dust hid in the galactic outskirts, adding mass where light seemed scarce. But better telescopes, radio arrays, and eventually spaceborne instruments sharpened the picture until the embarrassment became undeniable. The outer reaches of every spiral galaxy sweep around as if embedded within a vast, spherical halo of matter that emits no light, absorbs no light, and betrays its presence only by the gravitational tether it keeps on visible stars. Picture the Earth inside a dark ocean whose waves you can never touch, a tide that moves through rock and bone and spacecraft as though they are not there at all. Dark matter is not merely dark, it is transparent. It does not clump into suns, does not ignite, does not reflect. It slips through our telescopes the way wind slips through a net. And yet, if you could weigh each galaxy, you would find that this ghostly substance outmasses bright matter 5-1. The evidence is not confined to rotation curves. When two galaxies drift together and merge, their clouds of gas collide and glow in searing X-rays, but the dark halos sail through one another without hesitation. Gravitational lensing, the bending of background light by mass, maps the true distribution of gravitating material in such merging clusters, and the resulting images reveal great bulging lenses of unseen matter displaced from the glowing gas. Again, the luminous stuff is the minority, swept along like froth on an invisible swell. Step back, and the same pattern repeats on the scale of the entire observable universe. Computer simulations that begin with the subtle ripples of the cosmic microwave background can grow into today's tapestry of galaxy clusters only if dark matter is stirred into the recipe from the start. Without it, structure would still be forming, the cosmos would be too young. With it, the filaments and voids we see in the sky fall naturally into place. Dark matter is the armature on which the visible universe is draped. What it is made of remains unknown. The familiar particles that build atoms, electrons, protons, neutrons, feel light, electricity, and the nuclear force. Whatever constitutes dark matter feels none of these. It interacts, so far as we can tell, only through gravity and perhaps the feeblest handshake of the weak nuclear force. A touch so slight that detectors buried deep underground have captured only ambiguous murmurs in the decade-long wait for a direct hit. Supersymmetry, axions, sterile neutrinos, each theoretical candidate is a name for our ignorance dressed in mathematics. The surest statement we can make is humbling. The greater part of matter's orchestra is playing instruments we have never held. While astronomers were still absorbing the ascendancy of dark matter, a second, deeper mystery surfaced. In 1998, two independent teams gauging the brightness of distant stellar explosions, type Ia supernovae, found them dimmer, and therefore farther than the expanding universe should have allowed. Something was accelerating the cosmic expansion, stretching space faster than gravity could break it. The measured effect is subtle on human scales. A galaxy 100 million light-years away recedes a few kilometers per second faster each year. Accumulated over billions of years, however, that gentle pressure compounds into an exponential escape. Galaxies that now grace our telescopes will one day cross a horizon beyond which their light can never reach us. The universe is not only expanding, its expansion is speeding up. Cosmologists call the agent of this acceleration dark energy. It is not a substance you can bottle or weigh. It appears as a property of empty space itself. Einstein's general relativity allows such vacuum energy, and in fact predicted it, though he famously dismissed the idea as his greatest blunder. Observations now resurrect the concept with a vengeance. Dark energy contributes roughly 70% of the total budget of the cosmos. Ordinary matter, the elements of stars, planets, and living cells, accounts for less than 5%. The universe we know is a shimmer on a dark sea, expanding under the pressure of an unseen swell. Together, dark matter and dark energy form what we might call the dark side of gravity. They are not anomalies tacked onto an otherwise tidy picture. They are the dominant actors in the cosmic drama. Their gravity bends light, governs rotation, binds clusters, and shapes destiny, all while remaining invisible to every instrument tuned to light or heat. We infer their presence because gravity is faithful. It cannot hide. A planet tugs, a star deflects, a beam of light detours, and from those minute deviations we reconstruct the hidden mass. Gravity has become our dark lantern, revealing what our eyes cannot see. The humility this demands is profound. Every census of the cosmos written before the late 20th century was a census of the luminous minority. Our brightest theories, our most cherished equations, were built upon a sliver of reality. It is as though a naturalist, having explored an island shoreline, proclaimed the whole continent known while an unexplored interior lay shrouded in mist. Efforts to illuminate that interior continue. Particle colliders race protons to near light speed, hoping to shatter them into showers that might include dark matter fragments. Underground laboratories cool crystals of germanium and xenon to millikelvin temperatures, listening for the faint recoil of a passing WIMP, weakly interacting massive particle. Space telescopes map the gravitational distortion of distant light, tracing the distribution of dark matter across billions of light years. The European Space Agency's Euclid mission, the Vera Rubin Observatory in Chile, and NASA's forthcoming Nancy Grace Roman Space Telescope will widen this gravitational cartography until it approaches the scale of the observable universe itself. Yet some researchers wonder whether the answer lies not in new particles, but in a deeper understanding of gravity itself. Modified Newtonian dynamics, or MOND, proposes that at extremely low accelerations, those felt by stars in the outskirts of galaxies, gravity grows stronger than Newton's inverse square law predicts. In this picture, dark matter is an illusion born of applying the wrong equation. MOND and its relativistic extensions can reproduce the flat rotation curves without invoking invisible mass, and they do so with disarming economy. But they struggle to explain the rich phenomena of gravitational lensing and the growth of cosmic structure unless further assumptions are stitched in. So far, no modified gravity theory has matched the comprehensive success of cold, dark matter when confronted with the full range of observations, though the race remains open. Perhaps the most tantalizing possibility is that both perspectives hold partial truths. Dark matter may be real, and gravity may yet reveal new faces in regimes we have scarcely probed. The coming decades will tighten the net. Sharper lensing maps, deeper underground quiet, and ever more precise measurements of the cosmic expansion. If dark matter particles exist, their discovery would crown particle physics with a new zoo of entities, rewriting textbooks and perhaps gifting technologies we cannot imagine. If they do not, then the burden falls back on spacetime itself, obliging us to reformulate the law that has guided planets since before the sun was born. Until then, we live in a universe whose greater portion is hidden, a reminder that nature is under no obligation to align with the categories of human thought. We are like sailors who, having learned to read the wind and waves, suddenly notice a deeper current running counter to every chart we possess. We can feel its pull in the turning of galaxies and the hush of accelerating space. We can name it, weigh it, and map its contours, but we cannot yet open its heart. What we do know is that gravity, the force we once believed we understood, has turned its unblinking gaze back upon us, inviting us into a darkness luminous with possibility. And so, carrying our small lanterns of curiosity, we step forward, following the bending of starlight into the next unknown. Imagine a star. Not just any star, but one whose mass rivals 30 of our suns, compressed into a sphere you could still cover with your outstretched hand if only you could survive its surface. For 10 million years it burns, forging heavier elements in its core, a slow heart transplant from hydrogen to helium, helium to carbon, carbon to iron. Each conversion buys time, but the price is the star's own gravity, patiently waiting like a creditor. When the core finally fills with iron, an element that cannot be coaxed into releasing energy, the star's internal fires wink out in a heartbeat. There is no outward push left. Gravity falls inward, and because nothing can stop it, it keeps falling. The infall accelerates into a collapse, then into a cataclysm. The outer layers rebound, the star tears itself apart in a supernova so bright it can outshine the galaxy that hosts it. Yet deep inside, something stranger happens. The core, the inner few Earth masses, keeps compressing. Electrons are rammed into protons, forming neutrons. Neutrons are squeezed until they touch. The density climbs past the density of an atomic nucleus. Space itself buckles. In less than a second, a new object is born, not made of matter in any familiar sense, but made of warped space and time. A black hole. We call its surface the event horizon, though there is no surface at all, merely a boundary drawn by light itself. Cross it, and the fastest thing in the universe is no longer fast enough to return. The horizon is not a wall you would crash against. You would pass it without a jolt, without a sound, without even a tremor underfoot. Yet once inside, every future path curves inward, toward a place we still name only with mathematics. The singularity. In truth, we do not know what waits there. Physics as we possess it falls silent. Picture the horizon as a sphere whose radius is set by a single quantity, mass. Stuff more mass inside, the sphere widens. A black hole the weight of Mount Everest would be no wider than a single atomic nucleus. One the mass of a galaxy's central monster would engulf the orbit of Neptune. The formula is simple, but the consequences are bottomless. Outside, you can still orbit. Inside, even to hover is impossible. The black hole does not pull harder than the star that preceded it. The difference is that every scrap of its mass now sits inside a volume so small that space folds back on itself like cloth pinched in a fist. Approach and time begins to hesitate. Bring an accurate clock and hover just outside the horizon, send a second clock home to Earth. After a year of your life, centuries may have passed on the distant world. The effect is not illusion. Your heartbeat, your thoughts, the half-life of radioactive atoms in your blood, all tick more slowly compared with the universe you left behind. Tarry too close, and you could return to a planet that has forgotten your language. This is gravitational time dilation, Einstein's gift to the imagination, measured today by satellites that must correct their own clocks lest our GPS maps drift kilometers off course. A black hole is the most perfect macroscopic object we know. It can be described completely by three numbers: mass, electric charge, angular momentum. No mountains, no valleys, no magnetic storms, no seasons. A black hole is bald, featureless, yet it remembers everything that ever fell in: mass, spin, charge, nothing else. The information seems lost, and for half a century this loss has haunted physicists, because quantum mechanics insists that information, like energy, can neither be created nor destroyed. Stephen Hawking found a way out, or at least a crack in the wall. By marrying quantum uncertainty with the geometry of the horizon, he showed that pairs of particles can steal energy from the black hole's own gravitational field. One partner falls inward, the other escapes. To the outside universe, the escaping particle carries positive energy. The black hole shrinks by a compensating amount. The glow is called Hawking radiation, faint as a candle on the moon seen from Earth. Yet it implies that black holes evaporate slowly, inexorably, perhaps finally exploding in a whisper of gamma rays. A stellar mass hole would take 10 to the 64th years to vanish, far longer than the present age of everything we see. Still, the principle matters. Even black holes are mortal. We have never watched one die. The cosmos is too young. But we have begun to watch them live. In 2019, a planet-wide array of radio dishes, synchronized by atomic clocks accurate to billionths of a second, turned Earth itself into a telescope. For a week, astronomers collected light that had traveled 55 million years, light emitted by gas spiraling at half the speed of light around an object in the galaxy M87. The image they reconstructed is not a photograph in the ordinary sense. It is a map of shadows, a silhouette of emptiness against a brighter ring of superheated plasma. The dark center is the event horizon silhouette, 2.5 times wider than the horizon itself, a distortion of space so severe that light rays are bent into a perfect halo. The picture looks like a fiery eye gazing back across deep time, and in a sense it is. We are seeing gravity unmasked, stripped of every convenience we once imagined. No solid ground, no surface tension, merely the pure geometry of bent spacetime announcing itself in light. Smaller black holes speak in a different voice. When two of them spiral together, they shake the fabric of space itself, sending out ripples that travel at light speed, compressing and stretching distances by a fraction of the width of a proton. In 2015, the LIGO antennas in Louisiana and Washington state felt such a tremor, a chirp that rose from 35 to 250 cycles per second in a fifth of a second, the signature of 30 solar masses converted into gravitational energy. During that instant, the collision released more power than all the starlight in the observable universe combined. Yet by the time the waves reached Earth, they lifted the mirrors of the detector by less than 1,000th of a nuclear diameter. We are learning to hear with instruments built on the scale of cities, and what we hear is a drumbeat of black hole heartbeats echoing across billions of light years. Still, the deepest questions remain whispered. What becomes of the information encoded in the matter that falls inward? Does it re-emerge in the subtle correlations of Hawking radiation? Or is the universe keeping a ledger we have not yet learned to read? Some calculations suggest that the horizon itself is a kind of hologram. Every bit of the star that collapsed pasted as data on a two-dimensional surface, the interior volume a mirage. Others propose that the singularity is avoided by quantum pressure, that what forms instead is a Planck-scale nugget, a fuzzball rather than a point. Until we possess a quantum theory of gravity, these are stories told in partial alphabets. Yet black holes are not merely laboratories for thought. They are gardeners of galaxies. The energy released by gas falling toward a supermassive black hole can quench or ignite star formation across thousands of light years, blowing buoyant bubbles of cosmic rays that rise like hot air through the galactic atmosphere. Without the regulating fire of black holes, Galaxies might have converted their gas into stars too quickly, too completely, leaving little left over for worlds like ours to form billions of years later. We are, in a very real sense, the ash of stellar fires tended by gravitational dragons we once feared and now cautiously befriend. Stand again beneath the night sky and try to feel the scale. Every few seconds a star somewhere collapses, and somewhere else a horizon winks into existence. The universe is filling with them, quiet, invisible, marking the edge of knowability. One day, far beyond the era of galaxies, when the last stars have guttered out and the cosmos has expanded into darkness, those black holes will evaporate, scattering light once more. The story will have circled back on itself. Matter compressed beyond recognition, released again as radiation, a slow breathing of space and time. We began by misunderstanding gravity as a force between things. We end by understanding it as the shape of the stage itself, a shape that can fold so sharply that it becomes a door. What lies through that door is not oblivion in the simple sense, but a region where tomorrow is no longer separated from today, where the distinction between here and there dissolves. To stand before such a threshold is to be reminded that knowledge, like light, has its own horizon. We map it, we honor it, and we keep walking, because the edge is where the next chapter begins. Imagine for a moment that the universe is not silent, not in the sense of sound waves traveling through air, but in the deeper sense that the very fabric of reality can tremble. A tremor not heard by ears but felt by stars. A shiver that passes through time itself, leaving behind the faintest echo of something vast and violent that happened long before our sun was born. Einstein first whispered of this echo in 1916. He had just bent space and time into a single, pliant sheet, and he realized that the sheet could carry ripples, waves of curvature racing outward at the speed of light. He called them gravitational waves. The mathematics was elegant, but the physical intuition was sobering. These waves would be so subtle that a galaxy might pass through one and scarcely notice. For decades, the idea lingered like a half-remembered melody, beautiful, probably true, yet forever beyond human reach. Then, on a September morning in 2015, two laser beams in Louisiana and Washington state slipped out of perfect step by a fraction of a proton's width. The distortion lasted 1/5 of a second. In that instant, the Earth itself stretched and squeezed by less than the width of a single atomic nucleus. No drum was struck, no trumpet blown, yet every cell in every living thing on the planet was imperceptibly kneaded by a passing wave. We did not feel it, but we captured it. A pulse of space-time, born 1 billion years ago when two black holes, each heavier than 30 suns, swirled together and merged into one. The energy they released was greater than all the starlight in the observable universe combined. Yet it escaped detection until it grazed our restless planet and whispered through an L-shaped tunnel of vacuum and laser light. We named the event GW150914, and we finally knew. The universe had spoken and we had ears. Listen again, more carefully, and the cosmos grows talkative. Since that first tremor, the detectors have grown quieter in noise and richer in signal. A second pair of black holes collided, then a third. Now the tally climbs past 100, each wave a fingerprint of vanished violence. The pitch rises as the orbits shrink, a quickening chirp that ends in abrupt silence, the sound of horizons meeting and becoming one. No light escapes such encounters, no particle, no radiation we have ever observed. Only the wave, rolling outward like a tide across an unseen shore, carrying news of gravity's most intimate embrace. Yet black holes are not the only drummers in the dark. When neutron stars, city-sized relics 1,000,000 billion times denser than Earth, spiral together, the finale is gentler but far more revealing. In 2017, Telescopes and interferometers recorded the same collision in light and in space-time. A cosmic chord struck in 2 octaves of perception. Gold, platinum, uranium, half the elements heavier than iron, were forged in that fire and flung across the night. We watched the sky change color, and simultaneously felt the universe exhale a wave that rattled mirrors in Italy and America. For the first time, we learned that cataclysm and chemistry can share a single heartbeat. How do we measure what no scale can hold? Picture 3 rulers, each 4 kilometers long, arranged in an L. Inside the vacuum arms, laser light shuttles back and forth, rebounding from mirrors so smooth that a bump the size of a DNA helix would be a mountain. When a gravitational wave passes, one arm lengthens while the other shortens, then they trade roles. The lasers keep count, counting in wavelengths of light, dividing distance into quadrillions of parts. The change we seek is smaller than 1,000th of the diameter of the atomic nucleus that makes up the mirror itself. To see it, we must silence the world. Ocean surf, passing trucks, the faint tremor of a distant storm, even the quantum jostle of the laser's own photons. All must be quieted, subtracted, understood. The result is a sensitivity so acute that the detectors can hear the random dance of molecules in the mirrors, a gentle thermal hush that mimics the universe's whisper. Distinguishing the cosmic from the earthly is an art more delicate than tuning a Stradivarius in a thunderstorm. What do these waves reveal that light cannot? They show us gravity in motion, not merely gravity at rest. By the time starlight reaches us, the drama is over. The actors have bowed and exited. Gravitational waves arrive like letters posted during the battle, still warm with gunpowder. From their shape we read the masses of the participants, their spins, their distance, their energy. We learn how tightly black holes can whirl before final merger, how stiff neutron star matter becomes under crushing pressure, whether gravity itself propagates exactly at light speed as Einstein insisted. Every measurement is a question answered, but also a new question posed. Some waves arrive sooner or later than expected, hinting, just hinting, that spacetime may have a subtle granularity, a quantum whisper we have yet to decipher. And there are tones we have not yet heard. Supernova hearts beat in silence only if they are perfectly round. Should the collapse wobble, the universe will ring. A lone neutron star, lumpy and spinning, will hum a steady note like a cosmic cello. The merger of a black hole with a neutron star may reveal whether the star is torn apart in a flare of matter or swallowed whole, quiet and swift. Further off, perhaps, the background surf of waves from the earliest galaxies will rise above the detector's noise. A slow, collective murmur of ancient black holes too small and too distant to be sensed individually. That murmur is already there, some calculations suggest, a tide beneath the louder events, waiting for sharper ears. We stand at the shoreline of an ocean we never knew existed, cupping shells to our ears and discovering that they still hold the roar of distant storms. Each new detector widens the aperture. Virgo in Italy, KAGRA in Japan, LIGO India soon to join. In orbit, the Laser Interferometer Space Antenna, 3 spacecraft 5 million kilometers apart, will listen to the baritone songs of million solar mass black holes as they merge in the hearts of galaxies. From that chorus we may learn how the great galaxies assembled, how black holes grew so massive so quickly, whether gravity whispers different laws across cosmic epochs. There is a quiet humility in this listening. The waves pass through us as if we were ghosts, yet we have learned to tremble in resonance with them. We are small, brief, and fragile, but we have become the ears of the cosmos, the memories of its loudest moments. In some far future, when the last stars fade and galaxies have drifted into darkness, these waves will still be traveling, weaker, longer, but undefeated by time. They will carry forward the story of what once was luminous and violent and alive. If anything remains to notice, It may feel the universe still humming the tune we first heard on a September morning when two black holes danced and the Earth itself sang back. And so we keep listening, not for fame, not for answers alone, but because to listen is to remember that we are part of the same fabric that trembles. The same equations that predict the waves govern the fall of every leaf, the turn of every planet, the beating of every heart. Gravity is not merely a force pulling us downward. It is the language in which the universe tells its story, and we, brief arrangements of atoms, have begun, haltingly, to speak it back. Gravity does not hurry. While the early universe blazed with radiation, the gentlest of all forces simply waited, patient, silent, irresistible. Time itself had to cool before gravity could begin its true work. When at last the cosmos dropped below 3,000 degrees, the fog lifted. Atoms of hydrogen and helium stepped out of the white glare, and the sky filled with a soft amber haze. In that amber, 1 part in 100,000 was slightly brighter. A patch here, a patch there, so faint that if you could have stood on the first morning of creation, you would never have noticed with your eyes. Yet those whispers of warmth were the seeds of everything we now see. Imagine a calm ocean under a night sky. Every wave top is level with every other to within the thickness of a leaf. Now breathe across it. The faint pressure of your breath raises corrugations no taller than a grain of sand. That is the kind of delicacy we are speaking of. Gravity felt those sand grain ripples in the cosmic ocean and began to pull. Where the gas was a touch denser, the pull was a touch stronger. Stronger pull drew in more gas, which increased the density, which increased the pull. A runaway began, elegant and slow. The universe was only 400,000 years old, yet the architecture of eternity was already being sketched. We still see the sketch. It has been traveling toward us for 13.8 billion years, light that last scattered when the cosmos was opaque. We call it the cosmic microwave background, a misnomer because it is not merely microwaves. It is a baby picture written on the sky. When we subtract the blazing stars, the restless galaxies, the din of radio chatter, what remains is a hush of ancient warmth. Measure that hush carefully, and you discover that some spots are warmer by 30 millionths of a degree. Those spots mark where gravity would later win, but warmth alone was not enough. The ordinary stuff of which we are made, protons, neutrons, electrons, can push back. When gas is squeezed, it heats, and heat creates pressure, and pressure resists collapse. For 100 million years, the primordial gas hovered in fragile balance, brightening here, dimming there, unable to fall all the way in. Gravity needed a silent partner. The partner arrived cloaked in darkness. It does not scatter light, does not collide with nuclei, does not warm by even a fraction of a degree. We call it dark matter only because we have no better name for something we cannot touch yet cannot ignore. It outweighs the visible universe 5 to 1, and it feels no pressure. While ordinary gas hesitated, dark matter streamed inward, forming vast translucent clouds that stood like statues in the sky. Within those clouds, the gas found refuge. Cool and sheltered, it could shed its heat as infrared glow, slip inward, and finally ignite the first stars. Dark matter was the scaffolding. Ordinary matter became the living tissue that clothed it. If you could watch the universe fast-forwarded, you would see the scaffolding grow. Filaments of dark matter stretch across millions of light years, intersecting in nodes where clusters will later gather. The whole resembles a sponge. Empty voids surrounded by walls and threads of matter. Time is the invisible hand tightening the weave. Gravity shortens the threads, thickens the knots, draws clusters into superclusters. What began as sand grain ripples becomes a web of galaxies so vast that unaided human eyes can see only the tiniest corner. We live on one of those threads, in a small knot we call the local group, itself an afterthought in the Laniakea supercluster, which itself is but one tendril in the greater web. To test this story, we build cathedrals of glass and silicon. Telescopes map the positions of millions of galaxies, measuring how their light is stretched by cosmic expansion. From such maps, we recover a three-dimensional scaffold. Where theory predicted a filament, we find galaxies strung like faint beads. Where simulations forecast a cluster, we see a swarm of old red galaxies drowning in hot gas. The agreement is unnerving, yet the maps are static. We still crave motion. Gravity offers another signature. It bends light. A galaxy's mass warps the space through which light from more distant galaxies must pass, turning each massive cluster into a crude lens. The background galaxies appear slightly squashed, their shapes aligned in arcs that center on invisible mass. By measuring the distortion across millions of such arcs, we reconstruct the dark scaffolding directly, independent of starlight. The result matches the simulations to within a few percent. We begin to believe that we understand the architecture, even while remaining ignorant of the architect. Inside the simulations themselves, galaxies bloom like frost on a winter window. Code written in dark rooms traces particles of dark matter and gas forward in time, step by cautious step. A single run may consume months on machines that could store every word ever spoken by humans. Yet the rules are spare. Attract, collapse, cool, form stars, explode, enrich, repeat. From such simplicity emerges spiral arms, bars, rings, warps, shells, an endless variety that no programmer ever hand-coded. Watch one simulation to the present epoch, and you will see a Milky Way twin, its thin disk laced with newborn blue stars, its center glowing yellow with ancient suns. Rewind, change the dark matter particle by a nuance, run again, and the galaxy grows fat and slow. A dull oval where life might never find enough heavy elements to build planets. The stakes of our ignorance are written across every sky we simulate. Still, the simulations remain incomplete. Put in too much ordinary matter and the central galaxy grows overly bright. Too little and the stars fade below what we observe. Somewhere in the recipes for turning gas into stars lurks a missing ingredient. Perhaps supernova winds blow farther than we thought. Perhaps supermassive black holes inject energy that stirs the gas like a spoon in tea. Perhaps the dark matter is not perfectly cold, but possesses some subtle pressure that smooths the smallest clumps. Each hypothesis leaves faint fingerprints on the web. Our task is to read those prints before they are erased by the expansion that pulls galaxies beyond our sight. Even now, the expansion tests gravity itself. On the largest scales, hundreds of millions of light years, space is stretching faster than galaxies can swim inward. Gravity still rules locally, but it fights a retreating battle. In another 100 billion years, observers in some distant galaxy will see only their own island, the rest of the web swept beyond the horizon. They will map the cosmos and conclude, wrongly, that they are alone. We are privileged to live while the evidence is still fresh, while the story can still be read in full. Consider the long chain from ripples to richness. A difference of 30 millionths of a degree became the Virgo cluster, whose gravity bends the paths of nearby galaxies and sends them drifting toward us at hundreds of kilometers every second. Those motions will one day merge the Milky Way with Andromeda, tearing spiral arms into stellar streams that paint new constellations across the night. Later still, the merged remnant will fall into the Virgo heart, and the web will tighten by one more knot. Each step is gravity continuing a song it started before there were ears to hear. We are latecomers to the performance. When Earth formed, the universe was already 9 billion years old. When the first humans looked up, the scaffolding had been fixed for 10 billion more. Yet the same force that assembled clusters also assembles us. Every heartbeat fights gravity, every footfall answers it. We are not outside the web, we are its brief, conscious threads. The calcium in our bones was cooked in stars that would never have existed had dark matter not provided the cradle. The iron that colors our blood was launched across space by supernovae whose gas could not have cooled without the scaffolding. We are not mere observers, we are the universe's way of reflecting on its own architecture. And still gravity does not hurry. It will still be here when the last star gutters out, when black holes evaporate, when even the faint microwave background has redshifted to silence. It will gather the ashes, slow the expansion, and, if the cosmos is destined to recycle, begin again. Between now and then lies our window, a moment when galaxies are near enough to map, when the night sky still speaks. We do not know how long the window will stay open. We know only that it is open now. A single strand of silk, hung in a quiet stairwell, can feel the weight of a falling leaf. So too can a thin wire, no thicker than a hair, feel the pull of the planet and the fainter tug of a nearby mass that weighs less than a raindrop. In the hush of a temperature-controlled cellar, the wire twists, almost imperceptibly, until two gleaming spheres, each the size of a plum, nudge it through an angle smaller than the width of a mote in a sunbeam. This is the Cavendish experiment, reborn in dozens of basement laboratories, still the gentlest handshake we have ever arranged with gravity. Students sometimes imagine the great astronomer himself in 1797, waiting by candlelight while his dumbbell of lead weights breathed against the cosmic tide. Today, lasers watch the reflection of a tiny mirror. Computers subtract the tremor of passing footsteps and the sigh of distant traffic. Yet the principle remains. If gravity can bend a wire, it can be measured, and anything that can be measured can be asked new questions. One of those questions is whether gravity keeps the same strength when it is crowded into a very small room. On our everyday scale, the force declines with the square of distance, so having the gap makes the attraction 4 times stronger. But what if, at millimeter or micron separations, the law quietly changes its mind? Theorists have suggested extra dimensions curled like sleeping cats alongside the familiar 3, or particles that carry gravity but are suppressed at larger distances by subtle quantum shields. To listen for such whispers, modern Cavendish balances have been miniaturized until the attracting masses are gold disks the width of a spider's leg, and the detecting fiber is a ribbon of silicon thinner than a soap bubble. When the disks are slid a hair's breadth nearer, any unexpected uptick in twist becomes a murmur of new physics. So far, the murmurs have not risen above the creak of the apparatus itself, yet each silence sharpens the boundary where Newton's law still reigns. If fibers feel gravity's slow breathing, atoms feel its drumbeat. Drop a cloud of cesium, cooled to within a whisper of absolute zero, inside a tall vacuum chamber. Pulse a pair of laser beams so the atoms split, recombine, and interfere like ripples on a dark pond. The two paths bend, not through space, but through time, because one route lies deeper in Earth's gravitational well by a few micrometers. When the atom waves meet again, the crests and troughs have slipped. The phase shift is a ruler whose units are not centimeters but femtoseconds of light travel. From this slip, we read the strength of gravity across the width of a single human cell. Repeat the drop 1,000 times while the moon wheels overhead. The drifting phase tells us whether Earth and Moon pull the atoms with exactly the same acceleration. No discrepancy has announced itself, yet the test tightens like a violin string, ready to vibrate at the smallest departure from equivalence. Even the quietest basement cannot escape the seismic heartbeat of the world, so we loft our experiments into the vacuum above the sky. The microscope satellite, a pair of concentric titanium cylinders the size of champagne bottles, circled Earth 14 times a day, free-falling together while sensitive electrodes asked whether their trajectories remained stitched to the same thread. Any difference in the pull of our planet on the two cylinders would have appeared as a ghostly voltage, rising and falling with each sunrise as the spacecraft passed from Earth's shadow into the glare of dawn. Across 2,000 orbits, the ghost never spoke. The accelerations matched to 1 part in 100 trillion, a test 100 times more stringent than any ground-bound cousin. Yet the cosmos offers still emptier stages. In the dead of interplanetary space, where solar wind thins to a handful of protons per cupful of vacuum, future craft will follow free-fall trajectories around the sun, their mirrors tracking one another with such exquisite calm that a displacement the diameter of a helium nucleus becomes a thunderclap. LISA, Laser Interferometer Space Antenna, will listen not for the creak of fibers, but for the long, slow chords of black hole collisions ringing across the galaxy. Each note is a ripple in space itself, and the way it stretches the triangle of spacecraft carries information about gravity in regimes where spacetime is bent into knots, where energy densities rival those of the Big Bang, and where our earthbound equations begin to tremble. While LISA waits in the future, another kind of antenna already stretches across the galaxy. Pulsars are city-sized spheres of neutrons that spin faster than kitchen blenders, their magnetic poles sweeping beams of radio light across the cosmos like lighthouses glimpsed through fog. By timing the arrival of these flashes to the span of a heartbeat across decades, astronomers have constructed a natural gravitational wave telescope the width of the Milky Way. When a long wavelength ripple passes, it compresses space along one arm of the celestial triangle and stretches another, nudging the pulses early or late by 10 millionths of a second. The measured irregularities, sifted from 40 years of data, form a humming limit on how often the universe's largest black holes embrace. So far, the background murmur remains below the threshold of a single persistent note, yet the silence itself is informative. It tells us gravity still obeys Einstein's score even when the stage is billions of light-years wide. Back in orbit, a more modest proposal is being sketched. SDE-Quest, a satellite carrying an atom interferometer cooled by the eternal chill of space, would drop rubidium clouds along an elliptical path that rises to 300 kilometers above Earth's surface before falling back. Across that swooping arc, the atoms would spend tens of seconds in free fall, an eternity compared to the blink-and-you-miss-it drops inside earthly towers. The longer the fall, the finer the split between paths, and the more precisely we can ask whether different isotopes of the same element fall at exactly the same rate. A violation, even at the level of 1 part in 10 to the 15th, would betray new fields that couple to mass in ways Einstein never imagined. Perhaps the same fields that might one day explain the shadowed mass we call dark matter. Each experiment is a conversation with the night conducted in the quiet language of null results. The wire did not twist beyond expectation. The atom's phase did not drift. The cylinders stayed their course. The pulsars kept their appointments. Yet every silence is itself a measurement, narrowing the corridor where new physics may still hide. We are like listeners in a dark forest, straining to separate the rustle of an unseen creature from the hush of wind. With every upgrade of lasers, every cooling of atoms, every smoothing of satellite orbits, we lower the volume of our own breathing so the forest can speak more softly than before. What would it mean if, one winter morning, a fiber twisted a fraction of a micron too far, or an atom's phase slipped by an extra thousandth of a fringe? It would mean that gravity, after 4 centuries of seeming the same everywhere, has moods, hidden strengths that surface only in the company of certain energies or distances. Such a discovery would not overturn the flights we launch to Mars or the GPS that guides us home. Those calculations are anchored in the domain where Newton and Einstein have already proven their reliability. But it would open a door to a deeper story, perhaps written in extra dimensions, perhaps in quantum strings, perhaps in something we have not yet imagined. The The door is not opened by thought alone. It yields millimeter by millimeter to the patient pressure of measurement. And so the laboratories keep their vigil. In the cellar, the wire waits, protected from the coughs of the city by layers of styrofoam and lead. In the drop tower, a lone atom falls in darkness, watched by infrared eyes. In the sky, spacecraft trace silent ellipses, their mirrors polished to a smoothness that would let a mountain pass through a valley with less than a ripple. Far beyond, dead stars spin down the seconds, their pulses crossing deserts of interstellar dust. All of them are asking the same question, whispered so softly that only absolute stillness can hear. Is gravity truly the same everywhere, forever and always, or is it only the first, familiar chapter of a longer tale? Perhaps the answer will arrive as a sudden tremor, a crack in the quiet. Perhaps it will emerge as slow as moonlight shifting across a wall, perceptible only when we look away and back again. Until then, we keep our instruments poised, our clocks counting, our hearts open to the possibility that the force we thought we knew best may still have secrets curled inside its heart, waiting for the gentlest touch to unfold. The sun has set behind the hills. On the darkening ridge, an observer tilts a small handheld telescope toward the first star of evening. The glass gathers a few photons that left that star years ago, and the watcher feels a familiar tug. The solid grip of Earth. Yet the same force that pins shoes to soil once guided those photons across the void, bending their trajectories by half a hair's breadth. We call the tug gravity, and we have lived with it for millennia, confident in its constancy. But confidence is not the same as understanding. The deeper we listen to the cosmos, the more the old melody of gravity slips into discordant counterpoint. Begin with the simplest question: why does gravity pull? In the fabric of space and time, massive bodies dent the weave, smaller bodies roll toward the dents. The picture is elegant and it carried us to the planets. Still, it is only half a map. Down among the atoms, where events are small and abrupt, another guidebook rules. There, particles are sparks of probability, flickering into and out of defined existence. Every other force has yielded to the quantum vocabulary. Electromagnetism, the strong and weak nuclear forces, all now written as exchanges of discrete messages. Gravity alone refuses the grammar. When we try to compress Einstein's smooth curves into tiny grains, the mathematics scatters infinities like sand. A working quantum theory of gravity would let us read the first instant of the universe, when all matter was squeezed into a space smaller than a berry. Without it, the opening pages of cosmic history remain illegible. Perhaps the trouble lies not in the equations, but in the stage beneath them. Imagine space not as a continuous canvas, but as a restless lattice of loops, or vibrating strings, or a dense foam of virtual connections. On the large scale, the lattice would appear tranquil. Only when we peer down to the width of a proton does the churning become visible. In such grains, space and time themselves might emerge the way temperature emerges from the jostling of atoms. Useful but not fundamental. If gravity is likewise emergent, then its directives are statistical, not elemental. It would be the thermodynamics of some deeper layer we have yet to reach. On such a layer, the distinction between past and future, between here and there, might dissolve, leaving us with a new set of landmarks. Meanwhile, the universe accelerates. Galaxies recede faster now than they did 5 billion years ago, as if emptiness were endowed with a relentless, tenuous pressure. We label the agent dark energy, but the name merely masks our ignorance. The simplest guess identifies it with the constant Einstein once inserted and later disavowed. Yet observations demand a value so small, 120 powers of 10 smaller than quantum theory naively predicts, that its tininess itself becomes a puzzle. A box of pure vacuum the size of Earth contains enough dark energy to lift a single grain of sand a millimeter each year. Multiply that modest push across the immensity of space, and the future is rewritten. Galaxies stretched beyond the horizon, starlight dimmed, warmth diluted until only darkness and silence remain. Whether the push stays gentle or strengthens with time depends on laws we have not yet uncovered. Some physicists suspect the missing chapter is hidden in extra dimensions. Picture the old sailor's map, a two-dimensional chart of coastlines. To its maker, the world is flat, ships vanish over the edge. Only by rising into the third dimension do we see the sphere. Similarly, our three spatial directions might be a brain, a sheet embedded in a roomier arena. Gravity, unlike light, could wander off the brain, leaking into the surrounding bulk. Such wandering would explain why gravity appears weak. Most of its strength drains away into directions we cannot point to. In the early, hotter universe, the leakage might have been even greater, altering the expansion rate, the synthesis of helium, the growth of galaxies. When the Large Hadron Collider slams protons together at nearly light speed, microscopic black holes might briefly flare, signaling unseen dimensions curled smaller than a nucleus. So far, the tunnels remain empty, but the search continues. Even without extra corridors, gravity keeps secrets on our own floor of reality. Drop a stone, it falls straight down. Yet the path is not perfectly vertical. As the stone descends, it drags time with it, twisting spacetime by an amount proportional to its angular momentum. The effect, called frame dragging, was measured by orbiting gyroscopes whose spin axes shifted by a few thousandths of a degree each year, a stately waltz that confirmed Einstein once again. But the same instruments hint at something else, a faint, persistent anomaly in the gravitational field of Earth, a few parts in a billion, possibly caused by a dark disk of captured matter within the planet, or perhaps by new interactions between ordinary mass and the quantum vacuum. The discrepancy is smaller than the tug of a child on an ocean liner, yet it whispers that gravity may have shades we have not catalogued. New ears are being built for subtler whispers. Later this decade, the Laser Interferometer Space Antenna will open 3 million kilometer arms across the void, sensing ripples from black holes spiraling into each other in the adolescent universe. On the ground, next-generation detectors cooled to near absolute zero will record the soft sigh of neutron star crusts cracking a billion light-years away. Each signal is a telegram written in pure gravity, unimpeded by dust or starlight. From their shapes we may learn whether gravitons, if they exist, possess mass, and thus whether gravity can distinguish left from right. Between the bursts, a persistent hum might emerge, the blended chorus of black holes too small to see individually, yet numerous enough to form a gravitational glow. Measure the spectrum of that glow, and we test the census of the cosmos more precisely than any telescope allows. Meanwhile, on tabletops, delicate experiments are lowering the floor of the possible. Torsion balances suspended by quartz fibers sense forces 1,000 trillion times weaker than the weight of a postage stamp. In vacuum chambers, cooled rubidium atoms are released like slow fireworks, their wave patterns interfering after traversing separate paths. A passing gravitational wave would shift the paths by less than the width of an atomic nucleus, yet the interference fringes would record the passage. Other devices hunt for violations of the equivalence principle, the ancient equality between gravitational and inertial mass. If a platinum ring falls even a trillionth of a percent faster than a silicon ring, the signal would betray new fields that couple preferentially to certain materials, perhaps the same fields that endow dark energy with its puzzling pressure. All these instruments share a single creed: precision is patience. Gravity is the weakest sculptor, but given eons it carves galaxies. Our task is to compress those eons into the brief span of a laboratory afternoon, to sift the quiet hiss of spacetime from the roar of terrestrial noise. Each null result tightens the lasso around theory, narrowing the playground of speculation. Yet every so often the needle quivers and the quiet turns eloquent. Consider the Pioneer anomaly. For 30 years, the two Pioneer spacecraft drifted outward, their trajectories mapped by the Doppler shift of their radios. A residual, tiny, persistent blue shift suggested they were slowing more than gravity alone predicted, as if the sun's light exerted an extra, imperceptible handbrake. The effect was only 90 parts per billion of the gravitational acceleration at Earth's orbit, yet it accumulated into thousands of kilometers of positional error. After exhaustive scrutiny, heat from the plutonium power sources, reflection of infrared radiation off the antennae, the recoil of outgoing radio beams, the anomaly dissolved into known engineering. Still, the episode taught us humility. A force we feel every second can still mask surprises when distances stretch to billions of kilometers and times to decades. What then of horizons far vaster? If dark energy strengthens, the universe may end not in fire or ice, but in fragmentation. Galaxies, then stars, then planets, then atoms themselves would be torn apart by the mounting repulsion, a finale called the Big Rip. The calendar for such a cataclysm depends on the precise equation of state of dark energy, the ratio of its pressure to its density. Current data leave the ratio within 1% of the critical value that separates gentle acceleration from ultimate disintegration. We balance on a seesaw whose pivot is hidden, or gravity may reverse its polarity on cosmic scales. Some models of modified gravity introduce a screening mechanism. Within the dense environs of the solar system, the force behaves as Newton decreed. Beyond a certain cosmic threshold, it changes sign, acting to accelerate expansion without invoking a mystical fluid. Distinguishing such a field from true dark energy demands cartography of the cosmos on scales larger than any yet attempted, maps that chart not only galaxies, but the voids between them, where matter is sparse and modified gravity would most readily reveal its hand. Back closer to home, the Moon still drifts 3 centimeters farther from Earth each year, a slow farewell measured by laser pulses bounced off reflectors left by Apollo astronauts. The recession rate encodes the combined tidal friction of oceans and the elasticity of rock. A deviation would hint at a variation in the gravitational constant itself, a possibility some theories entertain. After 50 years of ranging, the result is firm. If the constant changes, it does so by less than a trillionth per year, a stability that rivals the ticking of the best atomic clocks. Yet the very precision of the lunar measurement sets a benchmark against which any future theory must stand. So we stand between land and sky, between the certainty of weight and the mystery of expansion. Gravity has carried us from the fall of Galileo's weights to the swirl of galaxies, from the bounce of a ball to the slow death of starlight. Still, it withholds its final secret, why it exists at all. Is it a fundamental actor, or the echo of something deeper, the way temperature emerges from the hidden choreography of atoms? Will the next century reveal new fields that skirt the brains of hidden dimensions, or will simplicity prevail, the equations we already possess proving complete within the narrow range our lives can sample? We cannot yet say, yet the silence is not empty. It is the pause between heartbeats, the hush that invites the next question. Somewhere in a quiet laboratory, a laser stabilizes on a mirror cooled to its motional ground state. Somewhere on a launch pad, a rocket waits to loft a constellation of spacecraft into the dark. Somewhere on a chalkboard, a student erases a line and writes a new term, tentative, unexplored. These acts are small, but gravity teaches that smallness is an illusion of distance. Given time, the fall of a pebble can reshape a mountain. Given thought, the fall of an apple can reshape the cosmos. And so the inquiry continues, gentle, persistent, the only force we cannot shield against, the only force we cannot live without.